The GFCI test function relies on a ground path to properly trip a circuit breaker or outlet during a ground fault. In an ungrounded electrical box, the absence of a ground path means the test function might not work as intended. The 2000 Chicago Electrical Code, similar to the 1999 National Electrical Code, addresses GFCI installations in ungrounded locations. Specifically, Section 210.73 specifies that GFCIs in ungrounded locations must be marked No Equipment Ground. Section 210.8 mandates that GFCIs include a test button. National Electrical Code Section 406.3d emphasizes the need for periodic GFCI testing to ensure they are working. An inspector might argue that the test function is vital for ensuring safe operation, stating that even in ungrounded locations, there is still a risk of electrical shock and the GFCI should provide protection. The inspector might also point out that even a non-operational test function offers some level of protection. When engaging with an inspector, you can firstly explain the technical limitations, highlighting that the GFCI test needs a ground path, which isn't there in an ungrounded box. Secondly, cite the relevant code, pointing to the 2000 Chicago Electrical Code that allows GFCIs in ungrounded spots without requiring a working test function. Thirdly, discuss the safety benefits that the GFCI provides even with a non-functional test function, which is that it still provides electrical shock protection. If the inspector still wants a working test function, you might consider alternative solutions. One solution is to install a new GFCI in a location that is grounding. 2. You could replace the ungrounded receptacle with a grounded one. 3. You could install a ground rod near the electrical box. The core issue is whether the GFCI offers adequate protection even if its test function can't be reliably demonstrated due to the lack of a ground. The GFCI itself is designed to detect imbalances in current flow, which is a key indicator of a ground fault. It measures the current going to the load and compares it to the current returning. In a properly functioning circuit, these currents should be equal. However, if there's a ground fault, some of the current will leak to ground, creating an imbalance. When the GFCI detects this imbalance, even a small one like 5 milliamps, it quickly trips the circuit, cutting off the power and preventing electric shock. This functionality is independent of the test button. The test button simulates a ground fault by creating an intentional imbalance. When pressed, it directs a small amount of current to bypass the neutral wire and go directly to ground. This sudden imbalance mimics a real ground fault and should cause the GFCI to trip. However, without a ground connection, this simulated fault cannot occur, rendering the test button ineffective. The GFCI's primary function of detecting and responding to actual ground faults remains operational, offering significant protection against electric shock. This protection is crucial in older homes where grounding may be absent. While a working test button offers an extra layer of assurance, its absence doesn't negate the GFCI's ability to protect against real-world ground faults. It's important to understand that the presence of a GFCI, even with a non-functional test button, significantly reduces the risk of electric shock compared to a standard, non-GFCI outlet. GFCIs offer substantial safety advantages. While the test button offers a convenient way to verify functionality, the absence of a ground path in an ungrounded box prevents it from working. The primary protective function of the GFCI, which is to detect and interrupt ground faults, remains active. The electrical inspector's concern about the test function is understandable. The test function provides a quick and easy way to verify that the GFCI is working correctly. However, it is important to understand that the test function is not essential for the GFCI to provide protection against electric shock. As long as the GFCI is properly installed and functioning, it will still provide protection against electric shock, even if the test function is not working. The code allows for GFCIs to be installed in ungrounded locations without a functional test function, as long as the GFCI is marked No Equipment Ground. This marking indicates that the GFCI is not connected to a grounding system, and that the test function may not work. The GFCI is still providing protection against electric shock. Therefore, the electrical inspector should not require the GFCI to be replaced or repaired simply because the test function is not working. Instead, the electrical inspector should focus on ensuring that the GFCI is properly installed and functioning. This can be done by visually inspecting the GFCI and by testing it with a GFCI tester. A GFCI tester is a device that simulates a ground fault and verifies that the GFCI trips correctly. If the GFCI tester trips the GFCI, then the GFCI is functioning properly. If the GFCI tester does not trip the GFCI, then the GFCI may be defective and should be replaced. It is also important to note that GFCIs have a limited lifespan. Over time, the internal components of a GFCI can degrade, which can reduce its ability to protect against electric shock. Therefore, it is recommended that GFCIs be replaced every 10 years, or sooner if they are frequently tripped. Replacing a GFCI is a relatively simple and inexpensive task. It is important to follow the manufacturer's instructions when replacing a GFCI. When dealing with electrical inspections and code compliance, it's often helpful to consider various strategies for effective communication. First, it's crucial to approach the situation with a clear understanding of the relevant codes and technical principles. This ensures that you can articulate your position accurately and confidently. Second, maintain a respectful and professional demeanor throughout the interaction. This helps to foster constructive dialogue and demonstrates your willingness to cooperate. Third, be prepared to provide supporting documentation, such as code excerpts, manufacturer specifications, or technical diagrams. This can help to clarify your points and address any concerns the inspector may have. Fourth, actively listen to the inspector's explanations and ask clarifying questions to ensure you understand their perspective. This shows that you value their expertise and are committed to finding a mutually acceptable solution. Fifth, if you disagree with the inspector's assessment, calmly and respectfully explain your reasoning, citing the relevant codes and technical principles. Avoid getting into an argument or becoming defensive. Sixth, if you are unable to reach an agreement with the inspector, consider seeking a second opinion from another qualified electrician or electrical engineer. This can provide additional insight and help to resolve the dispute. Seventh, document all interactions with the inspector, including the date, time, location, and a summary of the discussion. This can be helpful if you need to escalate the issue to a higher authority. The situation with the GFCI in an ungrounded box highlights the importance of understanding both the technical aspects of electrical safety and the legal requirements of electrical codes. It also demonstrates the value of effective communication and collaboration with electrical inspectors. By combining technical knowledge, code compliance, and communication skills, you can navigate complex electrical issues and ensure the safety of your electrical systems. Electrical safety is a critical aspect of home maintenance and should not be taken lightly. Electrical shocks can cause serious injury or even death. Therefore, it is important to take precautions to protect yourself and your family from electrical hazards. There are several things you can do to improve electrical safety in your home. Firstly, inspect your electrical cords and outlets regularly for damage. Replace any damaged cords or outlets immediately. Secondly, avoid overloading electrical outlets. Overloading can cause the wires to overheat and start a fire. Thirdly, use ground fault circuit interrupters or GFCIs in areas where water is present, such as bathrooms and kitchens. GFCIs can help to prevent electrical shocks by quickly cutting off the power if a ground fault is detected. Fourthly, keep electrical appliances away from water. Water can conduct electricity and cause electrical shocks. Fifthly, never attempt to repair electrical appliances or wiring yourself. Electrical work should only be performed by a qualified electrician. If you are unsure about any aspect of electrical safety, consult with a qualified electrician. An electrician can inspect your electrical system and identify any potential hazards. They can also provide advice on how to improve electrical safety in your home. By taking these precautions, you can help to protect yourself and your family from electrical hazards. Remember, electrical safety is everyone's responsibility.